In this chapter, what we're going to be talking about is how we combine functions together. So let's say we take two functions f and g, and we want to arithmetically combine them. So like add or subtract or multiply or divide them. Basically, how we do this is we fix an x value, and then we find the y values that go with that particular x, and then we perform those operations just on the y values. So we don't, for example, let's say we have this point like 2 and 3 in f, and let's say in g we have the point 5 and 2, then it's not this. It's not like f times g equals 2 times 5, 3 times 2. Which would be like 10 and 6, right? So that's not what we do. The reason why we want to kind of keep the x's fixed is because our functions might represent something like profit and cost. So we might have like a profit function, p of x, and maybe a cost function, c of x. And what we might look for is a revenue function. So this profit might represent like dollars. I think what I actually wanted to do is write revenue for this one. Yeah. So if you know your economics a little bit, so let's say we have a revenue function. So this represents incoming money after X sales, and this would be outgoing money after X sales. So if we want to actually get the profit, it's revenue minus cost. But the X stays the same. I wouldn't want to like subtract the X's. It would be the revenue at X minus the cost at X. So we are actually just subtracting the outputs. For a given or a specific input. And so this is the context in which we use functions. So we don't want these operations to really do anything to X. They're just going to do things to the outputs. And that makes a lot of sense for the way that we use functions. So I mean, maybe even I'll stick with F and G. Let's just do some examples of this. I'm going to start with this lesson just doing point-wise ones, and then in the later lessons, I will kind of move on to the other types of combining functions. Yeah, it's kind of backwards in which ones are easier and which ones are harder. This is probably actually one of the harder ones. So let's say that f is just a collection of points. So -4 and 1, -2 and 0, 1 and 3, and let's say 5 and 4. And let's say g is going to be -2 and 1, and 1 and -1, 3 and 0, and let's go with 5 and 2. So they're both just a collection of points, respectively. My suggestion is to actually put these into a table of values. That's probably what I'll recommend for graphs as well. And so what I'll get here is my x's And so if you look, I've actually got 5 different x's listed. I've got -4, -2, 1, 3, and 5. And my f of x that goes with it, so that's the output for -4 for f is 1. We have -2 and 0, 1 and 3. I don't have anything for 3, so I'll just put a DNE for does not exist. And then 5 goes with 4. And then my g of x is going to be -2 and 1. So I don't actually have the -4 output, so I'll put a DNE there. I'll have 1 and -1, 3 and 0, and 5 and 2. And so what I can actually do is now just do my operations. So if I want to do f plus g of x, so I could write it like that. So if I am doing this in rough, so what I'll have here is it's the outputs that I'm going to add together. So that would be 0 plus 1, 3 plus -1, 4 plus 2. Now that I deliberately skipped over those other ones, we have a DNE. You can't do 1 plus something that doesn't exist. DNE, it doesn't mean 0. It means it doesn't exist. It's not in this realm of numbers. So we cannot perform that addition, which does mean that the output also does not exist. And I'll just clean up the other ones. My 0 plus 1 is 1. 3 plus -1 is 2. 4 plus 2 is 6. And so what I have here, if I wanted to actually write these things out, is my f plus g of my input is -2. It's equal to 1. And this one, f plus g of 1, sorry, is 2. And then the last one, I'd have f plus g of 5 is 6. And so if I wanted to put this back in the notation above, I would write f plus g, just this set of points, -2 and 1, 1 and 2, and 5 and 6. And likewise, if I wanted to multiply them, I could do basically the same thing. I might just restart my table there. Yeah, I can actually perform all my operations. If I want to do f minus g, I'd have 0 minus 1 is -1, 3 minus -1 is 4, 4 minus 2 is 2. If I want to do f times g of x, again, I'm just multiplying those outputs or those y values. So I can't multiply by something that doesn't exist. 0 times 1 is 0. 3 times -1 is -3. Does not exist. 4 times 2 is 8. And then similarly, f divided by g of x. Actually, what I might do is flip those ones around just to highlight something else that might happen here. Let's do g divided by f of x. I can't do something that doesn't exist divided by 1. Now 1 divided by 0, that's also a problem. right? That's not defined, so I'm going to write does not exist there. And then the rest of them, I'll have a -1/3 does not exist, and 2 divided by 4 will be 1/2. So I could actually write out the remaining list here. F minus G, F times G, and this one I flipped them around and actually did G divided by F. We could have done F divided by G and we actually wouldn't have had another problem point. Just do equals for all of those. Yeah, so F minus G is going to be -2 and 0. If I just read the column. 1 and -3. And 5 and, oh, sorry, I was reading the wrong. Sorry, I'm doing the F times G. Let me fix those. Sorry, F minus G is -2 and -1. 1 and 4, and 5 and 2. F times G is going to be -2 and 0. Right, I don't have to write the points that don't exist. 1 and -3, and 5 and 8. And in G over F, there's actually only the 2 points, 1 and -1/3, and 5 and 1/2. And so those would be my new, I could plot them as points or do what I want with them, but this is one way of describing these functions. So yeah, so this is how we can just do these things in tables and work with them this way. So that's going to wrap up this lesson. My next one, I'll make it a little bit more complicated by looking at graphs.